Today, in this video, we will see numerical on to find moment of resistance. Numerical is a cast iron beam of cross section resembling a rail is symmetrical about a vertical axis in cross section. Total depth is 180 mm, top flange width is 80 mm and thickness is 20 mm. Bottom flange width is 120 mm, bottom flange thickness 40 mm, wave thickness 20 mm and depth 120 mm. If the maximum allowable stress in tension is 30 Newton per mm square and that of compression is 50 Newton per mm square, find moment of resistance of the cross section. So, see this cross section, I cross section. Material of this cross section is cast iron. For rail purpose, this cast iron cross section made, and this cross section is symmetrical about this y-axis. See, right side of this y-axis and left side of y-axis both are symmetrical, but this I section is not symmetrical about x-axis. See, above this x-axis and below x-axis there is unsymmetry seen. See, this bottom flange is bigger, width is bigger 120 mm, thickness is also bigger 40 mm, and top flange thickness is 80 mm. Top flange thickness is 20 mm and width is 80 mm. So this I section only symmetrical about y axis, not symmetrical about x axis. Total depth for this I section is 120 plus 40 plus 20 mm. That means 180 mm total depth. Wave thickness is 20 mm. And problem statement for this numerical is to find moment of resistance for this cross section. So for solving this numerical, steps are, first step is to find position of neutral axis y bar for that cross section. Second step is to find moment of inertia. But in this moment of inertia calculation, we use parallel axis theorem because there is unsymmetry seen in x-axis. In our previous lecture, numerical 3, we have symmetry about x-axis. Top side of x-axis and bottom side of x-axis both are symmetry. So this numerical 3, we can't use parallel axis theorem. But in this problem, we don't have symmetry about x-axis, so we use parallel axis theorem. Next step is, after moment of inertia, we have to check shape stresses, and after this, with the help of bending equation, we find moment of resistance. So first, write data. Maximum allowable stress in tension, sigma c, is 30 Newton per mm square. Maximum stress, this 30 Newton per mm square can't be greater than this 30. That means tension stress limit is 30 Newton per mm square, and compressive stress limit is 50 Newton per mm square. And to find moment of resistance. Step 1. Position of neutral axis. Let us denote this bottom plane as 1, this wave as 2, and top plane as 3. So to find position of neutral axis, equation is y bar is equal to a1 y1. A1 is area of bottom plane and y1 is neutral axis to this bottom plane, plus a2 y2 for wave and plus a3 y3 for top plane, divided by a1 plus a2 plus a3. A1 is, see this bottom plane width is 120 mm and thickness is 40 mm, and this bottom plane is rectangular. So rectangle area B into T, 120 multiplied by 40, 4800 mm square. Y1 is neutral axis only for that bottom flange, and thickness of bottom flange is 40 mm. 40 divided by 2, 20 mm neutral axis from bottom fiber. Forty divided by 2, 20 mm. A2 is area of wave. Wave thickness is 20 mm and depth is 120 mm. That means 20 multiplied by 120 is 2400 mm square. Y2 is position of neutral axis for that wave part from extreme bottom fiber. So from this extreme bottom fiber to this wave neutral axis distance, that means this much. Thickness of this flange 40 mm plus this, that means this 120 divided by 2, this distance is 60 mm plus 40 mm, 100 mm. This much total distance is 100 mm. Right. 40 plus 40 plus 120 divided by 2. 100 mm. A3 is area for that top flange. Area for that top flange is, top flange width is 80 mm and thickness is 20 mm. And this top flange is also rectangle. That means 80 multiplied by 20 is 1600 mm square is area for that top flange. For that only top flange. 80 multiplied by 20, 1600 mm square. And Y3 is position of neutral axis for that top flange from bottom fiber. See, observe, we consider neutral axis from this bottom fiber distance. for this 1 also, for 2 also, and for 3 also. So distance from this bottom fiber to mid of this top flange is this 40 mm plus 1, this 40 mm plus 120 mm plus 20 by 2. One 70 mm. Put all these values in y bar equation. Four eight zero zero multiplied by 20 plus 2400 multiplied by 100 plus 1600 multiplied by 170 divided by 4800 plus 2400 plus 1600 is 69.09 mm is position of neutral axis from bottom fiber. In our previous numerical, remember we directly use 200 by 200 mm like this solving methodology for position of neutral axis. Why we use this methodology for previous numerical? Because in previous numerical section is symmetrical about x-axis, and in this numerical section is not symmetrical about x-axis. Upper side of x-axis and downward side of x-axis both are not symmetrical. That's why this y bar equation we use. Now next step is to calculate moment of inertia. Position of neutral axis is 69.09 mm from bottom. It means neutral axis for that I section is somewhere here 69.09 from bottom. X 69.09. And we have to calculate moment of inertia for this one bottom flange first. x1 x1. Next we have to calculate moment of inertia for this web part. Web part neutral axis is 60 mm, that means below this T section neutral axis. x2 x2 and last x3 x3. So first focus on bottom flange neutral axis, this, and moment of inertia for this bottom flange neutral axis. I is equal to I x1 x1 plus I x2 x2 plus I x3 x3. I x1 x1 axis is neutral axis of only that bottom flange part, and this x1 x1 axis parallel dimension are 120 mm. That means 120 as it is multiplied by 40 cube divided by 12 is moment of inertia for only this bottom flange rectangle. So write 120 multiplied by 40 cube divided by 12. And parallel axis theorem, for parallel axis theorem plus area for that bottom flange is 120 multiplied by 40. That means 4800, and multiply by distance between this T section neutral axis. See this green color x axis and only this bottom flange neutral axis x1 axis distance and square of this distance. That means this x axis and x1 axis distance between x axis and x1 axis distance is, see, this 69.09 minus 20 mm, because this 69.09 is from bottom fiber, and we deduct this 20 mm part because this distance is 20 mm. That means our this much distance is 69.09 minus 20 mm, 49.09 mm. So 49 49.09 square. This is parallel axis theorem for moment of inertia plus, and now next I x2 x2 for this wave part. So this x2 x2 axis similar dimension is 20 mm. That means 20 as it is multiplied by 120 cube divided by 12 is moment of inertia for only this wave part, and plus area of this wave part 2400, and multiply by distance between x axis and x2 axis. Distance between x axis and x2 axis is this distance, this 69.09 minus neutral axis, wave neutral axis is this y2 100. That means this x2 is above this 69.09. This x2 axis is not here. Someone here. x2 and from bottom fiber x2 distance is, see here, this a2 y2 is for wave and y2 is for wave 100 mm. That means distance between this bottom fiber to x2 distance is 100. And 100 minus this 69.09 is this distance between x-axis and x2 axis. 100 minus 69.09 is 30.91. So right, this wave x2 x2 is similar 20 multiplied by 120 cube divided by 12 plus area for that wave 2400 and multiply by 30.91 square plus for that top flange top flange x3 x3 axis similar dimension is 80 mm multiplied by 20 cube divided by 12 plus and multiply by this y3 is 170 mm. 170 minus 69.09 100.91 square I calculate this 4800 multiplied by 49.09 square plus 120 into 40 cube divided by 12. This is 2.20. That means 12.20 into 10 raised to 6 plus this second brackets 2400 multiplied by 30.91 square plus 20 into 120 cube divided by 12. 5.17 into 10 raised to 6 plus this third curly bracket 1600 multiplied by 100.91 square plus 80 into 20 cube divided by 12. 16.35 into 10 raised to 6. Therefore, this moment of inertia about x-axis for that I cross section is 33.72 into 10 raised to 6. And unit of this moment of inertia is mm raised to 4. Consider this beam as a simply supported beam because they don't give us any data in numerical. So consider this beam as a simply supported, and for simply supported, see here, simply supported, tension acts at bottom and compression top. So since the beam is simply supported, tension induced below neutral axis. yt is distance between neutral axis for that I cross section from bottom fiber. Yt is y bar. In step 1 we calculate this 69.09 mm. This is yt 69.09 mm. And this is yc and this is neutral axis. At neutral axis stress is 0. Stress at compression side, stress at tensile side. This yc is total depth is 120 plus 40 plus 20, 180 minus 69.09. Yc is equal to 180 minus yt. That means 180 minus 69.09 is 110.91 mm. And with the help of this triangle, similar triangle, write equation sigma c upon sigma t is equal to yc upon yt. And this step is check for shape stress. How we give this check for shape stress? We first consider this sigma t value as in numerical they have given maximum sigma t value 30 Newton per mm square. Consider maximum sigma t value 30 Newton per mm square and check this sigma c value comes as a greater than this 50 Newton per mm square or smaller than 50 Newton per mm square. Because we have yc, we have yt, we have sigma t, so calculation of sigma c is easy. Sigma c is equal to yc upon yt multiplied by sigma t. Yc is 110.91. Yt is 69.09. And sigma t is 30. Therefore sigma c is equal to 48.16. And unit is, this is in mm, this is in mm, and this is in Newton per mm square. Newton per mm square. So 48.16 Newton per mm square. And this 48.16 Newton per mm square value is less than maximum sigma c value. Maximum sigma c value is 50 Newton per mm square. That means this check is safe. This is safe in stresses. This I section is safe in stresses, safe in sigma c and sigma t. So next our main problem statement is to calculate moment of inertia. Now, for calculation of moment of inertia, use flexure formula. Now, using flexure formula, flexure formula is moment of inertia divided by, moment of resistance divided by moment of inertia is equal to stress divided by y is equal to E divided by R. Now see, we have stress, we have y, we have moment of inertia. So use this first equation, m by I is equal to sigma by y, and we have to calculate m. So m is equal to sigma by y multiplied by I, and sigma, use maximum y, always use maximum y. Between yt and yc, which is maximum? Yc is maximum, and when yc is maximum, then use sigma c. When we use yc, then we use sigma c also. So right here sigma c upon yc, because yc is maximum, so I choose yc, and when I choose yc, then I also choose sigma c. So m is equal to sigma c is 48.16 divided by yc is 110.91 and multiply by moment of inertia is 33.72 into 10 raised to 6. Therefore, moment of resistance comes 48.16 multiplied by 33.72 multiplied by 10 raised to 6 divided by 110.91 is 14.64 into 10 raised to 6 Newton mm. This is in Newton per mm square. This is in mm, and this is in mm raised to 4. So mm get cancelled. Here 3 comes. mm. So Newton mm is right. And that means this moment of resistance is 14.64 kilonewton meter is moment of resistance for that I cross section. Thank you very much.